It looks like you guys got all checked in. Man, there is a lot of things to talk about today. But this is one of these big questions that we think about. Maybe we'll address this here today. Man, what kind of water should you drink? See, when I was growing up, no one asked this question. I lived through this big transition in the world where people actually paid for water. Like, you guys are like, what? Of course you pay for water, because I want good water. I want vitamin water. I want filtered water. I want distilled water. I want alkaline water. I want beverages. I want flavors. I want all of this stuff in my water, and I'm willing to pay for it. But what baffled me when I was growing up was that people actually would pay for bottled water. They had nothing in it but water. And we now just take it for granted that you would pay for water. But then it becomes all of these questions. What should you drink? What is it about water? In fact, water has become a dirty word. Well, especially tap water. That kid's going to kill themselves. Drink it. Well, I don't know. It feels like when I drink from the tap, all of this stuff comes into my head. Was this a great topic? Everybody, woo! It's a hot topic, what we should drink and what we shouldn't drink here. And we are going to address some of that. But, I could be like my parents here who recently invested. This is a good deal. I think they spent more money. And people are paying big money to get pure water, to get water that meets some sort of standard that they think is awesome and will give them great health. And I have many stories behind this. This one's only $269. Oh, I'm sure the price has gone up. But we want to address today some of the most amazing properties of water. You see, in this series, we have talked about the different gases in the air. And one of the reasons why we have all these gases in the air is so that we can have liquid water. Because liquid water is one of the most amazing substances that has taught you bad chemistry. Because its properties, and many of them are unusual, and we've talked about them in class and even today, that other substances don't have. And so we will try to share and talk about some of that here today. And so there's a lot of things. I've come up with 14 here topics on the density, the polarity, the viscosity, melting points, heat capacity, and we could spend probably a whole lecture on each one of them. And we're just going to go through and talk about some of them here today. And so that we can understand why this molecule is so special, why it's so important, and why so many scientists are enthralled with studying water. It is so unusual. But when you drink it and you swim in it and you hopefully shower in it, we just take it for granted that it is common, ordinary, boring, old H2O, dihydrogen monoxide. 55 molar. No, we're not even going to talk about 55 molar today. We should. What I want to get started with here today, so I've got like 100 slides. We're just going to go, okay, good. We're going to just skip around on some of them. And we're going to talk about the fact that the water molecule is very, very small. This is a very important property of it. I have some measurements here, some different ions that are actually a little bit smaller, kind of drawn at the scale a little bit. So water is one of the smallest molecules that we know about, one of the smallest compounds, which means multi-element. It is made of oxygen and hydrogen, and these are some of the smallest elements on the periodic table. It is small. Why is that such a big deal? Well, because if something is small, you can do some interesting things with it. In fact, you can separate it from other molecules that are much larger. This turns out to be a very important property of living systems. And so I'm going to come back to this in just a second here. I am going to make a little project here that you can do at home. It's kind of fun. And I'm going to make an osmotic pressure system. What is that? Well, it turns out because since water is so very small, it can be filtered through a special membrane that only water can go through, and other ions and molecules cannot go through. So because of its small size and its other chemical properties, it can be separated out and purified, and it could be done, dare I say, naturally. Or perhaps someone designed a system in which water could be purified. So what I'm going to do is, what's shown on the slide is what's called a semi-permeable membrane. And if you can create what's called a concentration gradient, something where you have a lot of ions or molecules on one side of a semi-permeable membrane, and then you put essentially pure water on the inside or on the other side, you can get water to go back and forth, and it will try to dilute the really highly concentrated side. But where do you get semi-permeable membranes? Well, it turns out they're everywhere. And one of them is the good old carrot. This is a semi-permeable membrane. It's what the plant uses to go inside the ground to get water to go inside and to then go up inside the plant. And so I'm going to simulate that process today with this. So I'm going to put this in some water here. And I'm just going to use good old tap water. And we're going to put some water in here. And with this water, I'm going to put this carrot, but I need it to sit in the water, so I'm going to just make it a little bit smaller. Okay, so that will sit in there. Oh, that's pretty good. We can put more water in there. Now, what I'm going to do to illustrate the property, I'm going to put a highly concentrated sugar solution, okay, hopefully it'll come out, inside of this carrot, and that's going to create a concentration gradient where the water wants to go and dilute that substance, and the water is going to go in, and we're going to see that take place. Now, in order for that to happen, though, I need to be able to get inside the carrot and put this highly concentrated solution. So I brought a drill, and my parents are probably disappointed that I'm not building anything more interesting, but I am going to hollow this out and make a little bit of a mess here. And let me just cut the top off. And the carrots won't last too terribly long. Oh, yeah, that's a little bit better. So I'm just going to drill this out. I've matched this with my system here, I think. Did I put the right one on? I think so. And so, so I just drill. Ooh. All right. Drill out the middle of the carrot. It goes pretty easy since it's not wood or metal or anything. And so I've drilled out the center. Okay, there we go. And I'm going to create a system here with some tubing. And this will go inside, and it'll be nice and tight. And then as water is drawn in, it will go up inside the tubing. In fact, you can make this go uphill. And that's how a tree does it, or a plant, to get water upside. They use this very special property of moving water uphill. Okay, and we may actually set it down to the side here. So, okay, this is doing good. So now I'm going to put some of this sugar solution here. Now, we could put salt and all sorts of things in here, but I like to put sugar in there. This is corn syrup, because all sugars come from plants. Sugar is all natural, okay? Because it all comes from plants. Does that sound bad? Our health person down here. Sugar's all natural. Come on, Mom. It's vegan. It comes from a plant. That's why we shouldn't use the word all natural. Okay, because there's good things in nature, and there's healthy things and there's unhealthy things. So, man, that's a big hole. Okay, so I wanted to get that in there. And I think, normally I put a little bit of food coloring because it's a little hard to see. But I think what I'm going to try to do is I'm going to simulate what a plant has to go through. I've never done this before. I'm just doing this in front of you guys for the first time. I'm going to make my water dirty. Okay? And I'm going to see if it cleans it up. And so I'm going to keep it clear. And I'm going to press this in like this, and hopefully it will stay. And you guys are going to have to trust me here. Okay, and we're just going to put this in. And I didn't bring a marker, though. Man, I can't hardly see that stuff. I think it's up here. I may color it just because I can't see it very well. And we'll just see if it will still work in all this mess. All right, let's go ahead and color it, because it is just hard to see. All right, so I just put a drop of green in there. Very good. And we mix it all around. And I push it in. Oh, I got a bunch of clear. Now the clear stuff's on top now. That's all right. Okay, so we're going to push this in. Ah, there's some. And I'm going to set this off to the side, which is probably bad for our camera here. But we're going to put this down here. And we're going to see, and I'm going to tape it up. I brought some tape. And we're going to see, I had to do this one first because it turns out this process is very slow. And it could take our whole time. So we're not going to watch this. But we have in the past done some what we call osmotic races with this. And you can try different root vegetables and things. And it's going back down in there because my stopper, I think, is not fitting in there very good. And it's all wet and slimy. All right. All right, stop. It's going down first. All right, so we're going to let this go. And the water is going to move inside. And hopefully we'll see it. The level's kind of, it's reaching some kind of equilibrium here. Stop. It's right here, and it's going down, 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 because it's trying, the stopper's not fitting in there very good. All right, so it might go where my little mark is. Okay, really good. All right, so as water senses this difference between what's inside and what's outside, the water's going to go inside, and the water in the, oh, it's right where my marks are, and will start to go up in the tube. This is exactly how a plant clears up water and purifies it. Why? Because water is so small. And it can go through the semi-permeable membrane called the roots. So you can do this with potatoes and carrots. I don't know what's another root vegetable. Beets. Beets would be great. And you could do races with each other to see who can go the fastest and to move water up into a tube. So we did this with our chemistry class, or it was a Vespers actually, many years ago. And we moved about an inch or two in an hour. I won, though, by the way, with the carrot. The carrot seems to work really well. And just saying. This can generate a lot of force to move uphill. And my general chemistry students are going to do this calculation next semester. And so the water moves from the low concentration side to the high concentration side, and it purifies it in the process, or it could purify it, depending on how we do it. So it's so important that the plant is making sugar because that creates a highly concentrated solution on the inside, and hopefully it's clean. This osmotic pressure can be calculated using something that looks a lot like the ideal gas law. In fact, it's based on the ideal gas law. No surprise in some ways. We're not going to do it. You need to know the concentration of the stuff inside. You need to know the temperature, some Van Hoff factor. Oh, the gas constant. Oh, we see that before in our class. The temperature in Kelvin. That's why the Kelvin scale is so important. And it can create a lot of pressure to move water uphill. Well, how much pressure can it create? It is amazing. It can create enough to go up into these really tall trees that are hundreds of feet high. And when I've done the calculation, I'm not going to do all of it for you. I use 7.66 molar corn syrup because that's what it is there. And I'm able to calculate a pressure of 187 atmospheres that system can create. That means it can go up 170 atmospheres worth of pressure, which turns out to be about a mile up in the air. This can create enough force to move water up a mile. Okay, 1 atmosphere can move water up 34 feet, 2 atmospheres 68 feet, so on and so forth. And so when we do the math, this has a lot of pushing power. That's amazing. Why? Because water is small and can go through this semi-permeable membrane right here. That's amazing. Okay? So there is plenty of pushing power to push things way up high into a tree. So I have all the directions here. Use corn syrup, and you can see some of the things here. So this is fun to do at home. Try different vegetables and root vegetables. You can try different things besides corn syrup. Try salts and different things, and you can move water uphill. And it's all based on the property of water being very small. All right, so very important property there. Now, let's see, what should we do next? I think the next thing that we're going to do with water, because it also takes a little bit of time, is I'm going to try to boil some water here. Now I'm going to take the same, I'm not going to do a whole lot because it takes water a long time to boil. I'm just going to take some good old tap water. And I want to get this boiling because we're afraid of tap water. I'm not really sure why. I can understand people's aversion to it. So I don't have my striker here that we have in lab. I think I turned that on. Yep. Okay. So we're going to get some water boiling. Perfect. Okay. Now we want to watch this over time to see what happens to this water, to this tap water. Now some of you in lab who have done this, if I let more oxygen in there, it'll be hotter and we'll go faster. We're going to watch what happens to tap water when you boil it, and over time you're going to see something happen. This is good. You can do this at home with good old tap water. I wanted to make sure you saw me do that so you can see I'm not using anything special. Just good old tap water, Andrews University, purchased by this from the city of Berrien Springs. I think we use Berrien Springs city water now. Okay, why is that so special? Water is very good at dissolving salts and minerals, and this is actually pretty loaded with minerals. And why is that? So we are going to talk about that for a little bit. And I think we'll start with this part right here. All right, and this will lead us into our discussion. All right, lightning. What is lightning? Electricity. Shoo! Right? And when people see lightning, they say, run for cover. Don't go anywhere that is near trees or power lines, right? You want to stay away from that. And what do they say about water during a lightning storm? You should avoid or go swimming. Right, yeah, don't go swimming, right? Because if lightning hits water, water, is it conductive or not conductive for electricity? Water is typically conductive. Now, many of you guys have seen this already, but we want to highlight this again. So we avoid water, because it's conductive, the high ground, open spaces, and metal, of course. Anything that conducts and is tall, because lightning will hit it. So we want to stay away from all of that stuff. Okay. Why do we avoid water? Because it conducts electricity, or does it? All right, and so actually I think we're going to do that part now while that's cooking. And so I'm going to move this off to the side. And I have my conductive experiment that I've done for my class before. I'm not sure Dr. Novak's class has done it. I'm going to get that out of the way. And so, I have my life and death situation here. And we are going to do some fun things with water and to see if it conducts electricity or not. And I hope I brought there's my water right here. And let's make sure. Okay, we got our water there. I am rinsing it. Rinsing is very important, lab students. Otherwise you won't get the effect that you're looking for. Okay. All right, so we have some good old water right there. And we are going to create a life and death situation here by plugging this in to the outlets. Okay. Okay, danger, danger, danger. Life. Video in here, let's make sure this works. Okay, woo, it works. All right, so if something is conductive, it will close the circuit and make the light bulb turn on, like water. Like water. Like what? Why is not this water? I thought water conducts electricity. Why is that?
There's no ions in it.
Very good. There is no ions in it. That's still dangerous. So I'm just going to grab some tap water here, and let's see if tap water conducts electricity. Okay. Let's get that guy out of the way. Look, yeah, okay, it's conducting. It's not great, but there are ions in the water that are conducting electricity. There are no ions in here because my water is special. It's purified. We got it from the store. It's been purified by reverse osmosis, which is that process we just saw, but in reverse, because the water wants to move towards the high concentration, but you can move it away. All right. So many of you know that if we take something like salt in here, okay, and we mix it around, we can turn and make the water conductive. Okay? So when salt dissolves, it makes ions, and those ions then can conduct electricity. Water in itself is not conductive, only the ions that are in it. So all of these ions are, there's ions in tap water. We saw that it was conductive, so it is dangerous. Unless you had a pool of distilled water. If you had a pool of distilled water, you'd be pretty safe, okay? You wouldn't have to worry about it. Most people do not have this pool readily available, so don't trust that, okay? So is water really conductive? Well, not in and of itself. We have distilled it, or people distill it. This is one way. You can evaporate the water, cool it back down in this condensing column, and get purified water. And as you boil substances here, only the water is going to leave, and all of the ions will stay because they are salts and they have high intermolecular forces, and they will not evaporate. Okay, because they have the ionic force that is holding them together, and they'll eventually come together and form some solids, which is what I'm doing right here, and we're going to see that process at work with that. We make our own distilled water. You can buy it at the store, as we saw there. We can run this conductive experiment to see the difference between all of these things. We actually have made, and this is a note to my wife here, this was made here at Andrews University, and these are, let's see if this one works, little batteries with with LED light bulbs and a 9-volt battery, and you can put them in and watch them light up. See, that's much safer. And you're not at risk at, electrocuting yourself. And you can touch metal things to see if they're working or not. And so that's a lot of fun. That could be a nice little product to sell to homeschooling families. Just saying. Just saying. All right, our water is boiling. We knew that was going to take a while because it takes a long time to heat something with water. All right. So one of the important properties of water, then, is that it can dissolve salts. Now, this seems rather boring on the surface, okay? And the way that it works, as we've learned in our class, is water has this polar nature. It's both positive and negative, and it can surround these ions and dissolve them and separate them from themselves. And so they become dissolved. And so we just did that, and we saw that it conducted electricity. And so there are other ways to see if you, I don't think I brought this. I forgot to bring that. Is to test yourself to see if you are conductive or not. No, I forgot to bring them. All right, we have to go on. All right, one of the important things about tap water and water in itself is its ability to dissolve these different minerals so that we can get them in our bodies. There is not another substance that can dissolve these minerals quite as good. And I thought I had that slide coming up. But this is an analysis of our water from a few years ago. There is 163 milligrams of calcium in 1 liter of water. You can about get your daily requirement of water. You have to drink 7 or so liters, which is not, it's like a gallon of water. Quite a bit. But I've seen people with gallon jugs all the time here on campus. And but right now, that's quite a bit of calcium. Quite a bit of sodium, magnesium, iron, potassium, zinc, a little bit of aluminum. I don't know what that does for you. It doesn't do anything. Copper, your body needs a little copper, and nickel and manganese. And our water is delivering all of these things. And it is special in its ability to dissolve ions and move them around. And there is little to no other substance that can do it. And it is called the polarity or the conductivity or the polar nature of water. And I did some comparisons here with some other minerals here. And we just, okay, I guess I have that. All right. So here, that's our water. And I compared this with spinach. This was interesting, little project we did. Spinach has lots of potassium, sodium, magnesium, iron, lithium. I wonder why there's lithium in spinach. In fact, lithium is found in a number of green leafy vegetables. If anybody knows anything about lithium in the mental health profession, there's people who take lithium carbonate, and it's no different than the lithium that you find in plants. So I wonder, in fact, studies have been done on lithium the amount of lithium in water, in municipal water supplies, city water supplies, and they have shown in places in Texas where there is slightly elevated levels of lithium, that violent crime decreases. And actually, I think it was Austria over in England, or not, in Europe, they have done that as well, and have shown it. So various places around the world where there's elevated, not high levels, too much can be toxic, but there's reduced violent crime. That is very interesting. Wonder why there's lithium. So all of these elements here are in spinach. When you boil water and you remove the water, we found that the water took almost, just slightly half of the potassium, well, but it takes quite a bit of the elements away from the spinach. So if you boil your spinach in water, many of those minerals will go into the water, because that's where they dissolve, and they're in the water. So I actually drink the water as like a little tea from after, and then I eat the spinach, and I feel great. And I encourage you to do that. Maybe you do that, or maybe you don't eat spinach. Maybe you should be eating spinach. You feel, this is your dad talking. Eat your spinach, okay? You will feel better. You will do better. And if you don't eat that, eat some cabbage juice or drink some. I will talk about that in just a minute. All right. So it turns out there's actually more potassium in spinach than a banana has. The banana, for some reason, has cornered the market on the potassium industry. There's potassium in like everything. It's like sodium. It's everywhere. It's like a lot of these elements that are everywhere. Not just banana. Oh, man, I'm low on potassium. I got to eat a banana. No. Well, okay, banana probably tastes better than spinach. But you can, like any fruit and vegetable has lots of potassium and sodium in it. Man, our water is having a hard time boiling over here. That is crazy. All right. We'll let it go. Good thing we started it early. All right, so how much do you need? I actually did the calculation here real quick. And, yeah, you need to drink. Yeah, we already talked about that. So the amount of 160 milligrams in 1 liter of water, man, that's right up there with nuts. If you drink 2 liters, right, I mean, you'd be getting as much as some of these seeds and nuts and things. Now, it's hard to top getting your calcium from dairy products because it's been so concentrated in the milk products there. But you can see it's as similar to a lot of vegetables, lentils, and a variety of things. Just drinking water. Just drinking good old tap water, you can get quite a bit of your calcium, magnesium, and other elements that you need. You need all of those. That's so important for a variety of things in your body, including bones, because we always think calcium and bones together. All right. So this is definitely very important for life, and that we can dissolve things. So we're gonna let that go for a little bit, and maybe this is okay. Well, I think my last slide here was what other substances dissolve water. So I'm going to do that one real quick. Or dissolve salts. And I have in the slide right here the amounts of different salts that of sodium chloride that can dissolve in different solutions, solvents, that I have shown in my general chemistry class, so I thought I would put it up again. So in 1 kilogram of these different liquids, how much sodium chloride can be dissolved, and you can see water tops the list. There's things like formamide, which is very toxic, that does a pretty good job, but it's toxic, and it's deadly. Okay, and then we see some other things like propylene glycol and glycerin. They're not that toxic, but they're very viscous, and so they dissolve sodium chloride in an okay way. Formic acid, liquid ammonia, methanol, deadly, poison, shouldn't drink it, shouldn't touch it. Ethanol, you can hardly dissolve salt in there. Water is the only liquid that can move salts and minerals around. The other things are too toxic. The boiling points, the viscosities are way off, and so they become very poor substances for moving minerals around. Okay, we're taking a look at our time here. Man, look at this stuff. This is having such a hard time. I'm cranking the heat on this guy, and it is hardly even boiling. Well, perhaps this is as good as any time to talk about then the thermal properties of water. So we're gonna talk about that real quick. So water, as it turns out, well, that's not. Man, I jumped to does this in class. It jumped to a wholly different slide than I clicked on. water has an amazing heat capacity. And we're seeing this on display right now. Well, what's heat capacity? Heat capacity is the ability of a material to hold on to heat or to pass it through. Metals like aluminum, iron, copper, and silver and gold have very low heat capacities. The heat just goes right through that. So for those students in my class who need an answer to their homework tomorrow about metals, this is one of the properties of metals, is that they have very low heat capacities. Now you've got 6 more to find out. Okay? And so the heat capacity is very low for metals. They don't hold on to it. Things like plastic, which we use for insulation, have pretty high heat capacities. But one of the highest heat capacity substance is water. Okay? And we're learning, man, this is the problem right here. I showed this in class today. Water, when you're watching water, it feels like it never boils. Okay? So they say a watch pot never boils. All right, well, it actually does, and we're finally here. Well, why does it have such a hard time boiling? And that has to do with the heat capacity of water, which is around 4. That seems like a small number, but in terms of heat capacities, that's a very large number. And there are some other elements and materials that have slightly higher things, but when we think about them, they're gases, so they would be hard to build a living system off of these things. Ammonia is toxic. Lithium as a liquid metal, hard to make living systems out of that. Have slightly higher heat capacities. That heat capacity, maybe we already know this, but it's good to talk about. That's what keeps our body regulated with its temperature, so we don't get too high or too low, and we can keep a thermal equilibrium with our environment. And water, because of its high heat capacity, is able to help us regulate our temperatures very well. And it makes water very hard to boil. And we actually talked about the other barrier that's there today, and that's the enthalpy of vaporization. That's the energy to take it from a hot liquid into steam. And that is such a huge thermodynamic barrier that we're just having a really hard time getting over here today. And I'm surprised at how low that is. Now, the other thing that has a pretty high heat capacity is actually water as a solid. At a 2 is pretty hot. And in fact, that is a property that is very important to life as well, that water, as water, liquid, and as a solid, actually have really high heat capacities to help regulate not only our bodies, but the world around us. And that is a very unique and special thing with water. We are going to, and something that was very interesting, I'm going to set up the next experiment while you guys watch this little video here on the conquest of coal. In the United States history, understanding how things boil and move heat and actually remove heat and become cold has been very important. So there's a little short clip, that's a couple minutes, about the whole ice industry in the United States that I found very interesting, and it has to deal with the heat capacity. So let's take a look here in the conquest of coal.
Across the Atlantic, a Yankee entrepreneur had a very different philosophy. Frederick Tudor had a chance conversation with his brother that led him on a path to become one of the richest men in America.
The story goes at the dinner table, they were trying to decide what they had on their father's farm they could make money off of, and certainly there was a lot of rocks, but people weren't going to pay for that. So they came up with the idea of maybe ice, because some areas did not have ice. And it seemed kind of crazy at first, but it paid off.
When Tudor began harvesting ice from New England ponds, he soon realized he needed specialized tools to keep up with the huge demand.
We had the saws, and the saws were improvement over the old wood saws. They have teeth that are sharpened on both sides and set, so it cuts on both the up and the down stroke. The crew could clear a 3-acre pond easily in a couple of days.
Tudor's dream to make ice available to all was not confined to New England. He wanted to ship ice to hot parts of the world, like the Caribbean and the Deep South.
When Tudor first tried to convince shipmasters to put his load of frozen water into the ships, they all refused because they told him that water belonged outside the hull, not inside. So he had to go find other investors to get the money to buy his own ship, and he bought a ship by the name of the Favorite.
New England became the refrigerator for the world, with ice shipments to the Caribbean, the coast of South America, and Europe. Tudor even reached India and China. Watching the ice cutters working Walden Pond, Henry Thoreau marveled that water from his bathing beach was traveling halfway round the globe to end up in the cup of an East Indian philosopher. Tudor, who soon became known as the Ice King, began using horses and huge teams of workers to harvest larger and larger lakes as the demand for ice grew. During the latter half of the 19th century, the ice industry eventually employed tens of thousands of people.
Tudor became the largest distributor of ice, and he became one of the first American millionaires. And we're talking about one of his ships going to the Caribbean, giving him a profit of $6,000. Now, this is in a time period when people were earning $200 to $300 a year, the average family. So someone earning thousands of dollars was just inconceivable. And that would be losing 20% of your ice when it got there. There was still huge amounts of profit.
Tudor's success was based on an extraordinary physical property of ice. It takes the same amount of heat to melt a block of ice as it does to heat an equivalent quantity of water to around 80 degrees Celsius. This meant that ice took a long time to melt, even when shipped to hotter climates. What started out as a small family enterprise turned into a global business. Frederick Tudor had industrialized coal in the same way the great pioneers of steam had harnessed heat.
All right, and all of that is because of the heat capacity of ice and water. And we know this is so important for life, and you can do some amazing things with that. So the heat capacity of water, which is on display here with boiling, it's taken a long time here. We're going to try to let that go while we do our last set of experiments, and we are going to deal with the other great and amazing property of water that has to deal with pH. Now this is water, it's HOH. It is a hydrogen atom and a OH, which, if you think about it, is the hydroxide ion for those in my class. And these are the two things that make up acids and bases. Okay? And so our concept of pH literally is based on water. And we do these calculations more next semester in Chem 132, and we actually show where the whole pH scale comes from, and it has everything to do with water. In fact, the concept of pH doesn't make sense outside of the context of water because it is based on the amount of, it's literally the H that's in pH has to deal with the amount of hydrogen ions that are in a solution. And so if there's a lot, then we say it's an acid. If there is not a whole lot of hydrogen ions, there's always going to be more hydroxides. We say that's a base. And I have here with me some really concentrated acids and bases. And so I thought I would run an experiment that I think many of you may have seen, but we're going to do it again. And we have some strong base there, and we're going to put a strong acid. This is hydrochloric acid. Oh, there's some other stuff in there. I'm going to clean the flask. And we're going to watch what happens, and I see some stuff happening already with this right here, and I feel like I got some on my hand, so I should have worn gloves. But I have water around, and water will fix that. So strong acids and bases, they're so important because they can make reactions go faster, and they're quite deadly. This is aluminum foil with concentrated, fairly concentrated sodium hydroxide. It is reacting, forming hydrogen gas, which is the combination of two of those hydrogen ions, and it is going to town there, making a lot of bubbles. And it is reacting quite violently there. And this one, not doing so well. And I feel like some of it, it's going. All right, whoa, man, that base is really going. We're going to put a little bit more acid in there. Okay, this is hydrochloric acid. They're both at 6 molar, if my student prepared them at the right levels. And they are going well and working. So acids and bases, they're so important because they can accelerate chemical reactions. I think this one's starting to bubble. Ah, yeah, it's starting to bubble. Had to work through the outer coating sometimes. And these reactions are going fast. So regulating pH is very important because if you don't, chemical reactions can go too fast and can be too violent. So our bodies know this, and so they are good at regulating it. Wow, man, these things are going. So this is just regular tap water right there. The aluminum foil here is practically gone, and it has totally reacted with that sodium hydroxide, the strong base. And this acid now is really kicking in. Woo! And it's full steam ahead, literally, as it's boiling away in there. Wow. And yeah, that's why I don't do it too close to you guys. It's a bit dangerous in there. So these are very dangerous substances that when they're mixed with water, I'm going to put some in here, you cannot tell that they're in there. These things all look like water, okay? And they can be very dangerous substances. The osmotic carrot was really working well, but I think it came unplugged. And so these substances, when they're with water, man, you can't tell the difference with them. And I was thinking about putting my hand in there at one of them. And I can't tell. Would somebody, actually, this is where, Cameron, we're going to have you come back up again. I want you to scramble those for me. Just move them around. Careful not to bump that. All right. So I put some dangerous stuff in there, and he's going to move them around. I'm going to put my hand in one of them. Okay, so I don't know. And I forgot which one. Some of them look like they're a little colored, but I seriously don't remember which one was which. And try not to look. Okay. And so so I'm going to put my hand in one of those. I did put some pretty dangerous chemicals into 2 of them. Are we all set? Yeah. Okay. So I'm going to put my hand into this. Keep your heads not. Usually in the audience helps me out a little bit. Is this a good one? Is this good one? Is good? Okay. This. All right. Well, I could do that. I'm kind of thirsty though. So let me just think about it here. I got some cabbage juice that I made this morning. Yeah, that's. I can't. Wait, was that the right one or was that the other one? No, I made a couple of things here, and so let's see. You guys it's really not bad. And so I'm just gonna pour some in here, and in here, and in here, some in there. There we go. And that will allow me then, when I want to mix these around, to see what's in there. Now, this one had the sodium hydroxide in it because cabbage juice, when it reacts with strong bases, turns green and eventually yellow. But since it's diluted in water, it's not that dangerous. This one had the strong acid in it, but since it's diluted with water, it's not too bad. In fact, that's more of a purple color. I think that acid's not that strong. Let's go ahead and put a little bit more in there. Okay? All right, there we go. All right. Now we'll mix it around. Okay. You got to trust in the dilution properties of water. And then this one, I think, was the neutral one here, which has more of a bluish hue. Although, why is that looking green? Let's put a little bit more in there. Let's see if that's what it is. So by putting in an acid-base indicator, like cabbage juice, we can actually tell the acidic and basic properties here. And man, we are just getting to the good discussion here of pH scale. And if things have lots of the hydrogen ions in there, they're very acidic. And if they don't, they're very basic. And, okay, we're going to talk about neutral. Ooh. So man, I wanted to get into this, but I was taking time for everything. So alkaline water is water that has a high pH, and it is become one of those waters that people are willing to pay some extra money about. So I think we'll discuss this in our next topic when we come next Tuesday, we're going to talk about alkaline water, and then we'll talk about one other topic next time. So just before you go, our boiling water is not new. Man, it needs, when you boil it, you will see all of those salts come out, and it will start getting very cloudy, and you'll see the powders. And this one, I can't believe how long this is taking. Usually within a few minutes, you can see that. Yeah, so we're going to keep that boiling. And this, the stopper popped out, but it had gone up to here, but I think the stopper come out. So that can become a design flaw in there. And so we're going to keep monitoring that as well to see what happens. All right, so if you can turn in your sheets to me, that would be great.